Imagine, if you can, the deepest, darkest quiet in the universe. A profound emptiness between the great islands of light we call galaxies. And through that void, a single star is flying. It's not drifting. It is screaming through the nothingness at over 1,000,000 miles per hour, a tiny point of furious light on a journey to nowhere. This star is a castaway. It wasn't born in this lonely darkness. It was thrown out. Something incredibly powerful gave it a gravitational kick so immense that it escaped the pull of its entire home galaxy. It is an exile, forever banished to wander the intergalactic medium, the vast space between the star cities. But what could do this? What engine is powerful enough to fling a sun into the void? The answer lies at the heart of nearly every large galaxy, including our own Milky Way. It is a supermassive black hole. Now, when you hear black hole, you might think of a cosmic vacuum cleaner, sucking up everything around it. But that's not quite right. A supermassive black hole is more like the galaxy's gravitational anchor. It is an object with the mass of millions or even billions of suns, all crushed into a single point of unbelievable density. This immense mass doesn't just pull on things, it fundamentally warps the very fabric of space and time around it. Imagine a heavy ball placed on a stretched-out sheet. The sheet dips and curves. That is what a supermassive black hole does to space-time. It creates a deep, deep gravity well, and everything in the galaxy, in a way, orbits this central point. It is the silent, invisible heart around which the entire galaxy dances. But the dance floor near this heart is not calm. The center of a galaxy is a place of beautiful chaos. Millions of stars are packed into a space that would hold only a handful in our own quiet neighborhood. They swarm around the central black hole like brilliant bees around a hive, moving at incredible speeds. Here, at the center of our own Milky Way, astronomers have watched stars they call the S-stars. These are massive, bright stars that whip around our supermassive black hole, Sagittarius A star, completing their orbits in just a few years. One of them moves at up to 3% of the speed of light. This is not a serene, stately waltz. It is a violent, high-energy cosmic mosh pit, where gravitational encounters are common and orbits are constantly being twisted. And into this chaos comes our victim. But it is not a single, solitary star. The key to this entire story, the crucial ingredient for this cosmic ejection, is a binary star system. This just means two stars that were born together and are gravitationally bound to each other. They orbit a common center of mass, locked in a perpetual dance. Many stars in the universe, especially the big bright ones, are not alone. They have partners. This partnership is everything. A single star falling toward a supermassive black hole would likely just have its orbit changed, bent into a new path, or maybe, if it got too close, it would be torn apart. But it would be very unlikely to be thrown out of the galaxy entirely. The secret is in the dance of two. Now picture this pair of stars. For millions of years, they have circled each other, a stable, predictable system. But their combined orbit around the galactic center isn't a safe, distant circle. It's a long, plunging ellipse. An orbit that, by chance, is destined to bring them on a terrifyingly close pass of the supermassive black hole. This is the fateful plunge. As the binary system falls deeper and deeper into the black hole's gravity well, it accelerates to mind-boggling speeds. The two stars, still circling each other, are now a single projectile aimed at the heart of the galaxy. Their long, quiet dance is about to end in the most spectacular way imaginable, in an encounter with the most powerful gravitational object in their universe. The two stars, bound together for millions of years, fall faster and faster, a single point of light accelerating into the gravitational abyss. They are a system within a system, their own small dance now caught in a much larger, inescapable waltz with the monster at the heart of our galaxy. The pull is no longer a gentle guide. It is a violent summons. As they get closer, a new force begins to act upon them, something subtle at first, then overwhelming. It is the power of tidal forces. This isn't like the simple pull of gravity we feel from our sun. Imagine the supermassive black hole's gravity reaching out, The star in the binary pair that is slightly closer to the black hole feels a significantly stronger pull than its companion, which is just a little farther away. This difference in gravitational pull, this gradient across the tiny distance separating the two stars, is immense. It acts like an invisible cosmic crowbar. It doesn't just pull the pair forward, it tries to pry them apart. It stretches the very space between them, pulling on the near star with one strength and the far star with another, trying to break the bond that has held them together for eons. The dance becomes a desperate struggle. The two stars are being pulled forward at incredible speed, but they are also being stretched, distorted by this differential gravity. Their elegant orbit around each other begins to warp, to elongate, under a strain that no material, no force in their own small system can possibly resist for long. And here, we encounter one of the deepest challenges in all of physics, the three-body problem. In our universe, we can perfectly predict the motion of two objects orbiting each other, like a planet and its sun. The math is elegant and certain, but add a third major body, in this case, the two stars and the supermassive black hole, and everything changes. The system becomes fundamentally chaotic, not just complicated, but truly unpredictable over long periods. The intricate gravitational pulls from all three bodies create a complex, ever-shifting web of forces. The future path of any one of the stars is no longer a simple, repeating orbit. It is a dizzying, chaotic trajectory that can only be understood moment by moment. Now, the pair reaches pericenter, the point of their closest approach to the black hole. They are moving at a fraction of the speed of light, whipping through the most warped region of space-time they will ever encounter. The tidal forces have reached their absolute maximum. The cosmic crowbar applies its final irresistible pressure. And in that instant, something incredible happens. The gravitational bond that held the two stars together for their entire lives, the force that defined their existence as a binary pair, is simply overwhelmed. The tidal force from the supermassive black hole is now stronger than the star's own gravity. The invisible tether snaps. The two stars, once inseparable companions, are now independent objects flung onto new, wildly different paths in the heart of the galaxy. Their shared journey is over, ended by the sheer gravitational power of the central giant. They are no longer a system. And then, the great surprise. The universe must always balance its books, especially when it comes to energy. One of the stars, the one that was likely on the inside track during that final, chaotic swing, loses a tremendous amount of energy. It is captured. It cannot escape the black hole's pull and is forced into a new, tight, and lonely orbit around the silent darkness. In that final, terrible moment of closest approach, the bond is broken. The tidal forces of the black hole become insurmountable. One of the two stars is torn away from its partner forever. It is captured, pulled into a brand new, blisteringly fast orbit around the supermassive black hole, closer than Mercury is to our own sun. Imagine the finality of that. A partnership that lasted for millions of years, ended in a fraction of a second by a gravitational power we can barely comprehend. The dance is over. One star is now a prisoner, destined to circle the black hole for eternity. But its companion, the survivor, is now utterly alone and is about to receive a violent, impossible gift. So, what happens to that second star, the one that escaped the black hole's immediate grasp? This is where the laws of physics reveal their beautiful, brutal logic. The universe must always balance its energy. The energy the black hole used to capture the first star had to be taken from somewhere. It was stolen, in an instant, from the orbital energy that bound the two stars together. All of that stolen energy is transferred directly into the surviving star. Think of the crack of a whip, where energy travels down its length and is focused into incredible speed at the tip. This is a cosmic version of that. In a split second, the star is supercharged with kinetic energy, accelerating it to a speed so immense it can overcome the gravity of the entire galaxy. This is the gravitational slingshot. Now, this might sound like a fantastic story, something we've only seen inside a computer simulation. For a long time, it was just that, a brilliant theory of a process called the Hill's mechanism. But the universe is often more incredible than our theories. In 2005, astronomers found something astonishing. A star moving so fast that it was on a one-way trip out of our Milky Way galaxy forever. They called it a hypervelocity star. Its speed was measured at over 700 kilometers per second. That is fast enough to achieve escape velocity from the galaxy itself. This discovery was a watershed moment. It was the physical proof. The gravitational slingshot at the heart of our galaxy was not just a model, it was real, and it was actively throwing stars into the great intergalactic dark. So let's think about that star for a moment. The lonely traveler. For millions, even billions of years, it will sail through the vast, dark emptiness between the galaxies, an exile from its home, carrying the memory of its lost companion and its violent encounter with the supermassive black hole. It becomes a silent messenger, a single point of light in an ocean of darkness. This journey provides an incredible scientific opportunity. As the star travels out of the galaxy, its path is bent and pulled by the gravity of everything it passes. This includes the enormous, invisible halo of dark matter that surrounds the Milky Way. By precisely measuring the star's trajectory, we can use it like a tracer, mapping the distribution of this mysterious substance in a way we never could before. So this lonely star becomes more than just an exile. It is a message in a bottle, thrown from the chaotic heart of our galaxy. It carries with it the secrets of extreme gravity, the signature of its lost twin, and a map of the unseen universe. A single point of light on an endless journey, reminding us that even the most violent events can illuminate the deepest mysteries. And so the supermassive black hole, an object we associate with consumption and destruction, becomes an engine of discovery. It dissects a stellar pair with unimaginable force, keeping one and flinging the other across the cosmos as a gift to science. A fleeting testament to the immense and intricate power hidden at the heart of everything. But what of the star left behind? The companion, the one that was not thrown away? Its story is just as extraordinary, though it unfolds in the most dangerous place in the galaxy. This star is now a captive, bound to the supermassive black hole in an entirely new, incredibly tight orbit. It has become what some astronomers call a squeezer. The name comes from the immense gravitational squeezing it endures. With every orbit, which could be as short as a few months or years, the star is stretched and compressed by the black hole's tidal forces. This constant violent flexing generates tremendous heat inside the star, causing it to swell up and shine hundreds of times brighter than it normally would. It's a star being powered not just by its own nuclear fusion, but by the gravity of its captor. Observing such a star would be a profound discovery. It would act as a tiny probe, a beacon of light tracing the very edge of the abyss. Its orbit would allow us to measure the black hole's properties, like its precise mass and even its spin, with an accuracy we could only dream of before. We could watch space-time itself being twisted by the black hole's rotation. The consequences for the star itself are extreme. It lives a fast, bright, and violent life. This intense tidal heating can strip away its outer layers, and its rapid orbital dance sends out faint whispers of gravitational waves, ripples in the fabric of spacetime. It is a brilliant, temporary candle burning fiercely in the darkness, destined to be slowly consumed or eventually torn apart completely. Now, let's return our gaze to the lonely traveler, the hypervelocity star. What do we know about these exiles? Observations suggest they are often smaller, less massive stars, similar to our own sun, or even smaller. They are not typically the giant blue stars you might imagine. There is a beautiful reason for this, rooted in the physics of the gravitational exchange. When the three bodies, the two stars and the black hole, interact, the energy transfer is most efficient when the least massive object is the one that gets ejected. The heavier star is more likely to lose energy and be captured, while its smaller companion gains a massive amount of kinetic energy, the energy of motion, and is flung away. But what if the original pair wasn't two stars? The universe is full of variety. Imagine a star with a large planet, a gas giant, orbiting it. If this system made the same fatal plunge toward the galactic center, the same gravitational dance would occur, but with a different set of partners. The outcome could be even more fantastic. The black hole might capture the star and eject the planet at an unbelievable speed. This would create a hypervelocity planet, a world without a sun, hurtling through the intergalactic darkness at millions of kilometers per hour. A true orphan of the cosmos, forever untethered from any star. This reveals a hidden population of objects sailing the great voids between galaxies, not just stars, but possibly planets, cast out by these powerful gravitational encounters. They travel in near-total darkness, carrying the chemical signatures of the galaxy they were born in, becoming silent messengers crossing immense cosmic distances over billions of years. And so, we see how the supermassive black hole, often thought of only as a point of no return, is also a powerful cosmic engine. It is a sculptor of galactic dynamics. It not only pulls things in, but through the intricate laws of gravity and motion, it also launches things out, creating the fastest stars in the universe and sending them on journeys that defy imagination.